to the great work of the director of the museum, Ricardo Rubiales. So he will be here now to uh, open the conference, this part of the conference that is in the Museo La Luz. I will talk now in Spanish and English. Estamos aquí en este lugar extraordinario, gracias al excelente trabajo y la excelente disposición del director Ricardo Rubiales. Y él va a ser, nos va a hacer el honor de abrir la conferencia en este espacio, el Museo de la Luz. Por favor, Ricardo.
Muchísimas gracias. Si les parece bien, hablo un ratito en español y un ratito más chiquito en inglés. ¿Está bien? Les agradezco mucho que estén con nosotros y nosotras aquí en el Museo de la Luz. Este espacio UNAM nació hace 2 años y hemos estado trabajando para crear un proyecto público de la universidad en el corazón de Mérida. Como saben, el campus UNAM tiene 20 años. Tenemos 20 años con instituciones educativas dentro del estado y no teníamos un espacio público donde las personas del estado pudieran venir y conocer más de lo que hacemos en la universidad, y esa es un poco nuestra misión. Quiero contarles 3 cosas importantes del museo en el que se encuentran. El Museo de la Luz está destinado a compartir la ciencia y la poesía detrás de la luz. Y somos un espacio donde convergen todas las disciplinas. Somos muy cercanos a ciertas instituciones de la UNAM, por supuesto a la Dirección de Divulgación de la Ciencia, pero también al C3, que seguramente ustedes conocen, el Centro de Ciencias de la Complejidad, y a otros espacios como Universo de Letras, como Radio UNAM, que nos acompañan en muchos de nuestros proyectos y donde tratamos de cruzar siempre ciencia con otras disciplinas en una mirada mucho más compleja. El museo, a diferencia de los museos de México, por lo menos de Universum, digamos, tiene algunas características que les quiero compartir. Primero, todos los proyectos que tenemos son en maya. Todas nuestras cédulas son en maya, las audioguías son en maya y tenemos visitas especiales para personas mayablantes y todas las comunidades mayablantes entran gratuitamente al museo. Es un programa que se llama Mediación Comunitaria y en el cual recibimos el año pasado unas 20,000 personas. Por otro lado, tenemos un proyecto especial para personas con discapacidad dentro de este mismo marco y hacemos proyectos específicos para recibirlas y nos enorgullece ser el museo que lidera ese tipo de proyectos en este momento dentro de la red de museos, en el sentido que hemos recibido muchísimas comunidades y diseñamos exposiciones específicas para recibir a personas con discapacidad. Otra característica importante es que somos un museo que no trabaja exclusivamente con infancias. Fíjense que si revisan ustedes el mapa de los museos de ciencia en México, encontrarán que la gran mayoría trabaja con el sistema básico, con primaria y con algunos años de secundaria, pero nos hemos dedicado a funcionar con secundaria, preparatoria y universidad. Y eso también nos lleva a otro tipo de discursos y a otro diálogo con los públicos. Y es un experimento que estamos probando y que hasta el momento nos ha funcionado bastante bien. El año pasado recibimos 50,000 personas, lo que nos pone entre uno de los 5 museos más visitados de la ciudad. A veces estamos en el primer lugar, a veces estamos en el cuarto, pero siempre estamos fluctuando y lo que más nos gusta es que la mayoría de las personas son personas que vienen de la localidad. Y por último, quiero contarles que aparte de ser temporales y aparte de enfocarnos en la comunidad universitaria, también somos globales, locales en un sentido. La exposición, que después si ustedes tienen tiempo de ver, que se llama ICEL, Insectos Extintos y en Peligro, es un proyecto que hicimos en colaboración con el Museo Americano de Historia Natural. Pero lo que quiero subrayar con ustedes es que el nombre de la exposición en Yucatán está en maya. Porque nos sentamos con el equipo curatorial del Museo de Historia Natural, nos sentamos con el equipo de museografía y decidimos aterrizarlo de una manera local. Así que trajimos muchas comunidades mayas, armamos un jardín en la parte de atrás con polinizadores locales, con plantas regionales y hablamos mucho de la circunstancia de los insectos aquí. Entonces recibimos una exposición internacional, pero en un sentido la transformamos en un contexto local donde pudieran dialogar ambas cosas. Al Museo de Historia Natural eso le encanta, ustedes lo saben, y siempre todos nuestros proyectos tienen esa idea. Bueno, si quieren puedo dar una breve bienvenida en inglés, ¿está bien? I really welcome you and We are honored to have you here. The Museum de la Luz is a place for sharing the science and the poetry of light. And we always work with multidisciplinary ways of thinking and the complexity of thinking. It's a motion place, always in motion, always changing, always bringing something new and bring you the time and the opportunities to share in experience and to see from different perspectives. So that's what we want to do with the public. So muchas gracias. Thank you again for being here. Muchas gracias. Gracias. Gracias, Miguel.
So I would like to thank the I mean first I want to say a little bit something about how it happens. So I think all of us were scientists, and we all know how difficult it is to lead sometimes with administration. So it's really uh, it takes a lot of time. It's a problem, no? So I just want to tell them this time it was very easy. So I contacted Ricardo Rubiales and Sergio Gonzalez, and they did it very smoothly and very easy all the time from the first time with an excellent attitude, and so we are very pleased to have the opportunity to get to know them and to see how good they work, how the great attitude they have. So let me say that in English. So todos en Spanish, sorry. Todos están aquí, son todos académicos y todos nosotros hemos sufrido mucho el hacer, el tratar con a las administraciones, las autoridades, que hace que todo salga muy difícil, eso es complicado siempre. Y quiero decir que este caso es un caso excepcional. Nosotros contactamos al personal del Museo de la Luz, a Ricardo Rubiales y a Sergio González, y nos mostraron qué es ser una excelente administrador, una persona que quiere que las cosas funcionen bien, tiene ganas de que todo, de que se hagan cosas importantes. Nos ayudaron todo el tiempo. O sea, gentes como ustedes dentro de la UNAM son una joya, digamos, para todos nosotros. Y agradecemos enormemente toda la ayuda y las facilidades que nos brindaron. Estamos muy agradecidos con el director, Ricardo Rubiales, y también con el coordinador de eventos, Sergio González, que hacen un excelente equipo y nos ayudaron enormemente. Gracias a ustedes esto se puede hacer, y para nosotros es una gran aportación. Muchas gracias por ayudarnos y por estar disponibles todo el tiempo y por hacer esto posible. Muchas gracias.
Gracias. Muchas gracias. Gracias. Gracias, Miguel. Muchas gracias. Muchísimas gracias.
Well, I'm now the next speaker will be now the chairman of the session is not me. It will be Rafael, who is the one that he invited many some of the speakers. So let me just give the microphone to Rafael. So he will be chairman of the session. So then just.
Thank you very much. Welcome, everybody. Well, the opening session of today will be given by Volker de Siqueira Pedra from Sao Paulo, Brazil. And he will talk about mean field models and the CAC limit in quantum lattices. Please.
If you would prefer not to be transmitted in a file, then you would need.
Thank you very much, Rafael, for the presentation. Before I start, I would like to thank Miguel and all people involved in the organization of this wonderful meeting. It's really nice. It's a pleasure for me to take part in this meeting in honor of the 60th birthday of Volker. It's really a great thing for me. So I would also say something that I learned yesterday from Volker, a colleague of us, Hans-Peter Heinz, passed away a few weeks ago. And he was a colleague from Mainz. No? He was really a very nice person. I would like to use this occasion to honor his memory. Actually, the subject of today has a lot to do with our discussions in Mainz. So I would like to say this before I so. This talk, I will make a summary of two works. The first one, this non-cooperative equilibria of term systems, it's a collaboration with Robert Nabrul, year 2013. And the second one, 10 years later, is an application of this work on the problem of the CAC limit. I'll explain in a moment what it is. So in this first work, we propose a particular approach to equilibrium states of models with mean field interactions. We give a notion of equilibrium states using a variational principle, and then we realized that this variational principle is useful for the CAC limit problem. No? And so I put here in highlights the non-cooperative equilibrium because this is the relation with Hans-Peter Heinz. Actually, I presented partial results in Mainz to him, and he said to me, what you are doing is just a game theory. I was not aware of that. It's not my domain, so to say. And he gave me books from Jean-Pierre Robin about game theory. And indeed, it was extremely useful to see the problem in this point of view of game theory and use some tools of game theory. It was extremely useful, and it was the right setting to discuss this equilibrium states of fermion system. No cooperative equilibrium. It's some concept which is very important in game theory. Huh? So now, what it's about. So the CAC limit, as you probably know, is the following. So you consider some models, a model for particles. They could be fermions, bosons, whatever you want, with some short range interaction, with some range it's fixed. Let's say it's called lambda, the range. And then you compute the equilibrium state for fixed lambda, and then you let lambda go to infinity, and you look what the limit is. Huh? So this problem is very old. The first result is by CAC in the 50s. He considered a spin chain, which is an integrable model, and he just computed explicitly what the limit is. That's why it's called CAC limit. And then about a bit less than 10 years later, there were very good results by Penrose, Lieb, Leibowitz, for models that were not integrable in this limit. Limit for models that were not integrable. They were trying to give a rigorous justification for the vapor liquid phase transition. No? And this works by Leibowitz, Penrose, and others. They're very famous. No? So the problem is not new. It's an old problem. But now the point is we consider not the pressure as in the case of the previous works, or some derivatives of the pressure, for instance, magnetization, things like that. But you try to consider the whole equilibrium state of the system. No? And the point, another feature that is new in our work is that we consider interactions that are not purely attractive or not purely repulsive. The long-range part. You could have a short-range part which is whatever you want, but the long-range part is either in the previous works is either attractive or repulsive. And you consider the case where you could have both. Some component that's attractive, some component that's repulsive. So you have indeed two scales. You have the range of the attractive part and the range of the repulsive part. So you should consider two limits, so not just one limit. That's a new feature. And as the title says of the talk, we establish a relation between this limit and the mean field models, some mean field models related to the CAC model. So we prove that in some cases you get exactly the equilibrium states of mean field models. And so it's useful to understand what's this general structure of these states. That's the first paper, the 2013 paper. So let me start with general facts about invariant states. I will not have time to discuss the proof, but I will give some arguments that were important in the proof. So let me start just with some notation and some general facts. So we consider a lattice of any dimension. It's a discrete system, type B, for instance. And then use the usual notation. AX is the annihilation operator at the lattice site X. We could consider a spin index as well, but for simplicity, I just consider the space index, no? For notation. No? And these operators, as you know, they satisfy canonical anti-commutation relations. No? And the fermion algebra, or the CAR algebra, is just the C-star algebra generated by operators like that. It's the smallest C-star algebra containing all these operators. And then, as is usual, the number operator is this product. A star X is X. No? Roll in a moment. And now I would we consider homogeneous systems. They are systems that are invariant in space. So it's important to define translations in space. What does it mean for a fermion? A translation is some automorphism of the CAR algebra with the following property. So if you apply the automorphism at tau y in this generator AX, you get the generator A y plus X. So it shifts the space index. So you can prove this automorphism exists and is unique. No? And you can make the same consideration for permutations of fermions. So if you consider the group of lattice translations, you could consider the group of finite permutations. By technical reasons, it's important to consider finite permutations. No? In the same way. So the permutation pi permutes simply the index. Right? So now, just to recall, we say that an element of the C-star algebra is positive, it's a joint and has a positive spectrum. And a state for us is, as usual, is a linear function from the algebra to C, such that if you consider a positive element of the algebra, the rho applied on this A gives a positive number. Huh? And it's normalized. If you apply rho in the unit of the algebra, you get 1. Right? It's like a probability. If you consider the classical analog of this, it's just a probability matter in a sense. Huh? Right, but why should we consider these general positive functions? It's because we are considering homogeneous systems in space and in the thermodynamic limit. So you cannot represent reasonable states with density matrix or something like that. It's important to consider more general functions to be able to do things. Huh? Now, there is an interesting property. It's well known. If some function in a C-star algebra is positive, then it's always continuous. So states are always continuous. It's not part of the equilibrium. It's a consequence of positivity, actually. So the set of states that I denote with A, with this E, capital E, is a subset of the linear functions of the algebra that are continuous. Now we say that state is invariant if the composition of the state rho with tau y for any translation is rho itself. Composition of a state and an automorphism is always a state. And if we get always the same state, you say it's invariant. And you denote with E tau the set of all invariant states of this algebra. And similarly, you can define symmetric states. They are the states that are invariant under permutation, under finite permutation. So it's easy to prove that all these sets, set of all states, a set of invariant states, a set of symmetric states, they are all convex subsets of the linear functions of the algebra, and they are weakly weak-star compact. No? Well, no? And another property that's trivial is that the set of invariant symmetric states, it's a subset of the invariant states. We are not consider all permutations, only finite permutations. So a translation is not implied. No? Translation is a permutation, of course, but it's not finite. So this inclusion is not completely trivial, it's well known. And another property which well known is that the set E pi is a phase of this convex set E tau. It's an important property as well. And we denote the extreme points of the extreme states in these three sets by this call E. No? And as we know, we have a compact set, so by Klein-Milman, the extreme points of the sets generate in the convex sense the whole set. So it's important to understand what happens in the extreme points. So that's a very important issue here. And actually, the situation is much better than Klein-Milman. We actually have a very, very good representation of any state in this set by Choquet's theorem. It turns out that CR algebra is separable, and as a consequence, this space of states, they are all metrizable. And because of the metrizability of the sets, Choquet's theorem holds, which says that for any point in E, and same for E tau, E pi, no? There is a probability measure on the set E, such that the support of this measure is in the extreme states, and the whole state rho can be written as an integral with respect to this probability measure. So you have some convex combination in the sense of an integral. So Klein-Milman says you can approximate any state by convex combinations. Here you have that you can have the equality, but not with a convex combination, a finite one, but with some a sort of infinite convex combination given by a probability measure. This you don't have uniqueness necessarily. I will come to this point. Thank you for the question. This is the next slide. Yeah. This bar is a closure. In the weak star, always in the weak star. So it turns out that in these sets, E tau, E pi, the Choquet measure is always unique. So have a simplex in the sense of Choquet. And then you have other properties. For instance, the set of symmetric states is a Bauer simplex, meaning that the extreme states form a compact set. And more interesting, the set of all states and the set of invariant states, they are the so-called Poisson simplices, meaning that the set of extreme states are dense in the set of all states. It looks strange, but this property was very important in our proofs. And what's interesting for me, at least, is that this kind of object is universal in a sense. It's unique to a final homeomorphism. So any other simplex of this kind is a homeomorphism that is affine unique, right? And any Choquet simplex that you can imagine in the same space, of course, is equivalent in the sense of the existence of a final homomorphism to a face of the Poisson. So you have a copy of all possible Choquet simplices inside this Poisson. And as I said, this density property was essential in our proofs. Now let's discuss what the extreme states are. So we have exactly the same situation as in probability theory here. So let's define what a product state is. Product state is what the name says. So if you consider two observables, A1, A2, concerning two disjoint regions of the lattice, then rho acting on A1 times A2 gives rho A1 times rho A2. This joint is important, of course. And then people proved a theorem that is very unknown in classical probability theory, the Finetti theorem, is saying that the Finetti theorem says if you have some probability measure that is invariant under permutations, it's a kind of integral of product distributions, right? And the same is true for the for the quantum case, for the fermion case, and for other quantum case. The Finetti team is saying actually that combined with the Troquet, that the extreme points in the set of symmetric states, they are all products, right? So by Troquet, for any symmetric state, you have an integral over such states, right? And it was a fancy subject in 2000, more or less. The people realized that various results about permutation invariant models, they were actually simple consequences of this fact, because at the end, you reduce everything to product states, and product states, they concern only one point in the lattice, actually. So you convert some problem that's in infinite dimension in a problem that's of finite dimension. It's very useful for numerics, for instance, and also for proving abstract things. So one important feature of our work is that we realize that we don't really need the product property for proving many things that they proved in the year 2000, more or less, but their godicity is enough. So you can do more or less the same in the set of translation invariant states, not in the set of, not necessarily in the set of symmetric states. It's a bit more general. And for physics, it's important because the most important models from theoretical physics, they are not symmetric. They are not permutation invariant. They are only translation invariant. So this, I'll come to this. So in the set of symmetric states, being extremo means being a product. In the set of translation invariant states, being extremo means being ergodic. I will define this. No? It's a weaker property. No? So product is always ergodic, like in probability theory, but the other way around is wrong. No? So that, sorry. Yes, please. Not that way, because when you put in the model, in the mean field model, then you get some nonlinear term that mixes everything. So it's not really independent. Yes. So as I said before, the set of symmetric states, the phase of the translation invariant states. So in particular, any product state is extremo state of the translation invariant states. And then, of course, the product property is an extreme form of clustering, right? So you could ask, is there some weaker clustering property that's equivalent to being extreme in the set of translation invariants? And the answer is the same as in the classical case, ergodicity. So, of course, for product states, if we consider the Cesaro limit of this kind of quantity, this kind of operational function, so you take y in some box and you take the average and you let the box you let the side of the box go to infinity, then you get the product, this product of expectation values. It's trivially true. And as a consequence of von Neumann's ergodic theory, the classical one with the GNS representation, then you can prove that this quantity has always a Cesaro mean. It's not necessarily the product, but it has always a limit. And then you can define, based on what you know about classical theory, that the state is ergodic if this limit is always the product. It's a definition. And it turns out that exactly the states are the extreme states in the set of translation invariant states, exactly as in the case of classical systems. So it gives a lot of intuition. Many features of quantum systems are very similar to classical systems because of this kind of problem, right? So as I said, we managed to generalize results that were proven with the product property, only with the ergodic one. So this was an important point in our report. Now let me fix a very simple model to explain the result. I will fix some simple model, explain the result, and then I'll tell you how we can generalize it. So take any box of some length, and define this Hamiltonian here in the box. You have, as usual, some hopping term there. And now I have two terms. Actually, you see one term with this plus minus, but what's meant is that we have two terms. We have gamma plus with a plus sign and gamma minus with a minus sign. So in order to get a small equation, I have written like that, but you have two interaction paths, right? Sorry for that. This is my compromise. Maybe. Okay, I agree, but the other version was ugly. So, but I think you see what I mean. Huh? So you have some exponential decaying two-body interaction. You have some factor here depending on the range of the interaction, lambda. It's as usual. It's there in order to have the property that the energy, the interaction energy of one single particle with the other particles around is of order 1. It's usual scaling, no? So you have one term of this type for the attractive part, and another one with different lambdas for the repulsive, right? And okay, if lambda 1 and minus is 0, then you say that have a repulsive case. If lambda plus is 0, you have that trivial one. If both are different from 0, then you have the mixed case. These cases were not considered before, and this contribution of us. Now, if you have this sequence of Hamiltonians, box Hamiltonians, you can define an energy function in set of translation invariant states. Very simple way. You take some invariant state and apply it in the HL, in the Hamiltonian. It gives you the energy in the box L. You divide by the volume, and you take the limit. And this limit always exists, and defines an affine and continuous function in set of translation invariant states. Now, you can do a similar thing for the entropy. You localize your state in some box. You compute the von Neumann entropy for this box. So the state in the box is given by a density matrix. And then you divide by the volume, you take a limit. And then you realize it's an affine function again, but it's not continuous. It's only upper semi-continuous as usual. Yes? Oops. No, because you are in the lattice, so it's not really a no. It exists. In the lattice, things are much easier. I see what you mean, but don't have it. With fermions, with bosons, you have this problem. And in any case, also in the lattice. Yeah. So now you have energy function and entropy function. So you can define a free energy function as usual. Energy minus temperature times entropy. And this function now is affine and lower semi-continuous because S is upper, but you have a minus here. So this function now has minimizers, and you call the set of minimizers is omega. It depends on the parameters of the model. And these minimizers are the equilibrium states for the model. It's not just an abstract definition. You can prove, for instance, that if you consider a Gibbs state in a box, and then you take the thermodynamic limit of the Gibbs state, if the limit is translation invariant, then it's necessarily an element of omega. So it collects all translation invariant limits of Gibbs state. So it's not just an abstract definition. It's related to the physical problem. No? It's not very difficult to see this. Now, so as I said here, no? So now the short range case is just a case where I fix some lambda, plus and minus, which is order 1. So the range of the interaction is comparable to the lattice space, right? This is the short range case. And now long range for us means that we take the side, the range of the. So the short range case is order 1, but if you consider a long range case, it means that the range is very large as compared to the lattice space. But you can do this in many ways. One simple way is to take lambda of order L, so the size of the system is of the same order of the range of the interaction. It's the mean field regime, which is much bigger than 1, so the lattice spacing. Or you can take something which is less brutal, it's a bit more realistic. So the size of the system is much bigger than the range, but the range is much bigger than the lattice space. This is the CAC case, which in a physical sense better. No? And then we find, so as I said in the previous works, they only consider repulsive or or attractive, so they have only one lambda. And now we can consider two lambda. So and so you can do the following. You can take lambda plus much bigger than lambda minus much bigger than 1, or the other way around. It's not clear what to do. And there is a big difference how you do this. Now, of course, you could take L much bigger than lambda plus, which is of the same order of lambda minus. We try to consider this, but it's quite simpler. We don't really have results for this case. We have results for these three cases, but not for this. Now, what's the equilibrium state in the sense of CAC? Sense of CAC here means the sense of the previous work. So if you don't have this competition between plus and minus, you have either plus or minus, right? So for each lambda plus or each lambda minus, and the other lambda is 0, no? You take some equilibrium state that you wish, and then you take lambda to infinity and look to accumulation points, right? And these accumulation points are, by definition in our work, the long-range equilibrium in the sense of CAC. And the equilibrium state in the generalized sense of CAC is the same, but you take both limits, lambda plus and lambda minus, in one sense or in the other sense, right? And as I said, we have proven that it's very important how you take these limits. If you take lambda plus before lambda minus to infinity, then you get something. And the other way around, you get another thing. You get not the same. So one of both limits have a strong relation to the mean field case that I will explain in a moment, but the other limit, not really. So now, what's the mean field? We explained the CAC. What's the mean field? So mean field means L is of the same order of lambda. So you have this exponential term being of order 1, right? The x minus y is of order L, and lambda also L, so it's order 1. And lambda is order L, so this term is more or less 1 over volume, and this is more or less 1. So you could replace this by 1 over volume, right? So your mean field Hamiltonian is, you have this hopping term, and this interacting term is replaced by this double sum here, the densities, no? Your gamma over the volume, as usual, right? And then you can play the same game again and define an energy functional with these Hamiltonians in place of the short range one. And you can prove the limit exists again, defines on a fine functional, but now this function is not continuous. Again, it looks like the entropy, it's not continuous. And if the system, if the case that you consider is repulsive, you get a functional that's upper semi-continuous, and of course the attractive is then lower semi-continuous, right? So you do the same again. So you consider the free energy minus T times entropy. And in the attractive case, your free energy functional is again lower semi-continuous, because the energy is lower semi-continuous and minus the entropy also. No? So you have minimizers. The set of minimizers form a phase in the space of photon-dash invariant state. So it's very similar to the short range case. It's a more natural case. No? Now, if you consider the repulsive case or the mixed one, then this F fails to be lower semi-continuous. Actually, it's affine, but it's only measurable. It's neither upper nor lower semi-continuous. It's a measurable function. And now, of course, the existence of minimizers is not clear. Then we use a trick that's very well known in the EDPs. For instance, the variational approach to EDPs is to consider the so-called gamma regularization of the functional. So you take the best approximation from below, that's convex and lower semi-continuous. It exists. There is a best approximation. It's called gamma regularization. And then you consider this new function instead of the original one. Again, it looks like abstract trick to have something with some precise mathematical meaning, but it turns out that again, thermodynamic limits of Gibbs states in the box, they minimize the gamma regularization. So if you understand the minimizer of the gamma regularizations, you understand the large volume limit. Right. So it's the right object to look at. But now the gamma regularization is not necessarily affine. So your set of minimizers is always convex, of course, but it's not a phase necessarily of the set of translation invariant states. So you see that repulsive and attractive terms in the mean field part, they play different roles. As the attractive one does not change much the structure of equilibrium states, but the repulsive one, yes, it destroys the phase property. And it's responsible, for instance, for long-range order, things like that. Because the states, they could be extreme in the set of minimizers, but they are not extreme in the set of all translation invariant states, so you have long-range correlation. Even if you have unique states as minimizers. So, affine means that it's convex and concave simultaneously. That's all. So, 20 minutes, more or less, I think. Oh. So, one important thing that you have proven is the following. We have shown that the usual cut limit, it means we consider only repulsive or attractive, not the mixture, is always an element of this omega mean field. It's always a minimizer of the mean field function of this gamma regularization. So if you don't have competition, the mean field theory gives correctly not only the pressure, but also the equilibrium states of the cut limit. So in the previous work, as I said, by Penrose, Leap, and others, they proved that the pressure converges correctly. And for us, we can prove that the pressure is just the infimum of the free energy function. Right. So the results of Leap, Penrose, and others are saying this, but we proved a bit more. We proved that the minimizers converge correctly, not only the infimum. So to prove that you have pointwise convergence of the CAC in the CAC limit to the mean field functional, it's not very difficult, but of course it does not imply that that the minimizers converge, the pointwise converge. Because you have to work harder now. And then what you have proven is this on one side, and then you consider this mixture situation. No? And you prove that if you take lambda minus much larger than lambda plus, it means you take the limit lambda minus to infinity before the other one, then again you have elements in omega mean field. It gives again a mean field equilibrium in this order. But if you take this the other way around, not necessarily. Actually, it's even worse than that. We have proven that even the pressure is not correct. If you take this limit like that, you get not even the pressure by the mean field by the mean field model, by the usual one. Then, of course, you can change your mean field model in a sense to get the right thing. You can generalize a bit the notion of mean field, and then you get again the right thing. But the intuitive model, so to say, that's the one that I have shown a few slides before, does not give the right thing. In this case, it's still. Right. Now, okay, I explained these results in this very specific case of this simple model. Now, I would like to say a few words. How can I generalize this? How general is this result? Now, in this paradigm, in the simple model, we have that the short range interactions, they define some energy functional in the set of translation invariant states. So the generalization is we define, as usual, some Banach space of interaction in a way that each interaction phi defines a functional with the same property, affine and continuous. I don't have time to give details, but this procedure is the usual, no? And then you have your free energy. You consider again your minimizers and so on. Now, what happens in the mean field part? So we can prove that for the model that I give before, this mean field energy has this explicit form here. So the mean field energy of some state, rho, is the integral with respect to the Choquet measure associated to rho of this function here. So the square of the expectation value of the density at 0. You integrate over rho hat with respect to the Choquet measure times the coupling, right? So it's proved that. Now I use this structure to generalize thing, this mean field part. So you consider a Banach space of measures of finite variation in S1. S1 is the unit sphere of the space of interaction, short range interactions, right? And then you define the mean field energy in this way. So you consider the energy functional for the interaction phi hat acting on the state whole, right? Squared. And then we integrate with respect to this product measure. So the Choquet as before. And for the measure for the interaction, use this measure M that you choose here. This measures over interactions, right? So if you think if you take some delta measure here, no, or a sum of delta measures, no, you get exactly a finite sum of terms of this kind, right? But you could consider a more general measure for the sphere. So you have some kind of a kind of continuum of mean field terms in your model, right? The usual models refer to the delta measures. Say you get the usual ones, but you have this infinite these models containing infinitely many mean field components. Right? It's possible in this. Now, so for us, a mean field model is phi. So it gives the short range part, which in our model was simply this hopping term. So you can generalize. You can take a generalized hopping here or something more complicated, and then a measure in this sphere of the set of the space of interactions, which gives the mean field part. And then, of course, you can consider the Jordan decomposition of your measure. No? Yeah, some M plus minus M minus, and this corresponds to your gamma. So this Jordan decomposition is just the coupling of the repulsive part, the M plus, and the coupling of the attractive part of the terms, right? It's now a measure, not a number. Now, then you do the same as before. You define a free energy given a phi and a M, a measure M. So you take the mean field energy and the short range energy for the phi. This is again a phi, not necessarily semi-continuous. You consider the gamma regularization, so on. You do the same, and you get exactly the same. What I have explained here for this particular case, this model with two interactions, no, can be proven for this in this very general set. Now, let me see how much time I have. I would like to explain a bit about the structure of mean field equilibria, because as you have seen, the CAC limit is at least in two cases, mean field equilibrium. So it's a good question to understand how they look like, this mean field equilibrium, right? So one thing that you do is the following. So as I have shown here, sorry, we use this. Okay. So no, it's not this. So you had this interaction, this mean field part, this mean field energy here, no, that you generalized. It's not important. I missed the slide, but okay, you had this kind of term for the mean field energy. No? You integrate over some measure in the space of interactions and the Choquet measure for state. It's a complicated object because you need the Choquet measure. No? It's not clear given a state what's the Choquet measure, no? Right? So you make a huge simplification. You pretend that all your states are extremal. It means the Choquet measure is simply the delta measure in this case. So you get actually only the integral over the phi in this case. So we pretend everybody is ergodic, and we replace this more complicated term with this one. It's a crazy thing. But with this density of extremal states and so on, you can prove that if you do the simplification, you understand a lot about the equilibrium states, the whole set of equilibrium states in Paulo sense. But the new functional is lower semi-continuous, so you do nothing. You don't need the gamma regularization. You can consider minimizers, but it's not convex. It's some function, no? Right? It's semi-continuous, but lower semi-continuous, but not convex, not concave. Right, and then, but we could consider the minimizers, and they are called here nonlinear equilibria by obvious reasons. And you would define the set omega tilde as being the set of all minimizers of this new function. And it turns out that this new set, which is much easier to understand, is a subset of the whole set. And this set contains all extreme points of this previous set. So if you take all convex combinations of these points here, you reproduce the whole set. It's not. It could contain points that are not extreme, but it contains all points that are extreme. So if you know this smaller set, you know everything. And now it's where the game theory plays a role. We showed that we can classify the states in this omega tilde via some game, some non-cooperative, via the non-cooperative equilibrium of some game. And the game is defined as follows. No? We used ideas of Bogoliubov. We defined a notion of Bogoliubov approximation of mean-field Hamiltonians. It's the following. So you have your fixed short-range component, phi, which will be there all the time. And then you replace your mean-field term with some short-range term, which approximates, in a sense, the mean-field part. And it's like that. So you have to fix two parameters, which are now L2 functions with respect to m plus and m minus, this repulsive and attractive couplings. So you take your fixed one, and then you consider this integral here. You take your c's, no? C plus, C minus, no? Which are functions of the interaction. Multiply with the interaction, so a number times interaction. And you integrate this function with respect to m, which gives you an interaction, short range one, right? This integrals were defined in the sense of Volker, so on. Everything is nice, no? And we call this the Bogoliubov approximation for parameters c plus, c minus, which are functions, L2 functions. No? Now we define a payoff function out of these interactions. Is the following: is the g, which depends on two parameters, c plus, c minus. It's c minus the norm squared of c minus the norm squared of c plus, minus the pressure for the model with this short range interaction. No? The pressure is minus the infimum of the free energy, so it's minus the pressure at C, right? So it depends on C via the norm, so it's in a simple way here, but here's the dependencies, of course, very complicated. Now you have some effective short range model, you have to compute the pressure, and then you have some payoff. Then, of course, you could ask if you would like to define a game out of this. Say, okay, you have the repulsive strategy with C plus, the attractive strategy, with C minus, and you try to find a saddle point or a non-comparative equilibrium in the jargon of game theory, no? For this functional. And you see it's not possible, but because you can even find models showing that the infimum and the supremum, they don't commute. So no chance of having some saddle point here. But there is a trick from game theory, a kind of trick. You can make out some situation of this kind. You can define a new game where the supremum, for which the supremum and the infimum, they do commute. This is the so-called extended game. This is an idea by Lasry. It's a very usual argument in game theory. Is the following: instead of considering strategies, elements of some set and elements of second set, you consider elements of one set, and for the other set, you don't consider the elements of the set, but the functions from this set to the other one. So you are implementing here transfer of information. So instead of, you have two players, player repulsive and attractive, they choose some strategy, but they don't know what the other one has chosen, right? But here, one player chooses some strategy, and the other one, he knows what was chosen, and based on this information, he can choose his strategy. So there is some transfer of information. It's a special kind of game. And the point is, this new game has this new in this new situation, replacing the strategy by the functions. No? You get a commutation of supremum and infimum. But it does not mean that you have a saddle point. It's always true that this equality is correct, but it does not mean that this equality is attained by a saddle point. No? Now, the other point is we prove that you indeed have saddle points there. The set of saddle points I denote with by n, right? And the saddle points, this non-cooperative equilibrium of this game, they classify completely the states in this omega tilde in the following sense. So take any saddle point, any non-cooperative equilibrium there, and define the set of self-consistent equilibria for this saddle point, which means the following. You take equilibrium states for the short-range interaction given by the Bogoliubov approximation for the saddle point, right? But you don't take any equilibrium state, but only those such that the energy for the state as a function of the interaction gives exactly the parameter C, which is a function over interaction. You have some self-consistency here, no? Of course, it's not clear that such a set is non-empty, but it turns out it's non-empty. And we denote the set by this station here. And we can prove that the set of nonlinear equilibria, which gives all other equilibria for the mean field model, no? Is this joint union of this non-empty sets given by the self-consistent equilibria for these saddle points. And that's all. Thank you very much.
So as long as I understand the example, so you take which
Let me put let me. So the model is like this. Yes.
so you have one of not of the attraction, but now the same one.
So you could have different couplings, one coupling for the repulsion and coupling for the traction, and different ranges, right?
So they do not completely the same. But there is one that
No, so same Lego. What do you mean? You don't have spin, for instance, here, no? You just have two. Yes. You mean they both are comparable? No, we tried this, and this is very hard. We don't have any results for it.
But then you have lambda cross with.
You consider either one of the lambdas is zero, and then you take the only one to infinity. That's the old case, let's say. Or you take lambda plus before and then lambda minus, or the other way around. In both cases, you have results.
Let's say that you have lambda plus.
That's it. Yes.
What remains?
What remains? I see. Yes, the question is very good in the sense of these functionals. If you take this one of the limits, and not the other one, you get a mean field model with the short range part corrected by this limit. So you get some mean field model which is only attractive or only repulsive because the other part is already away by the limit, and a correction to the short range part. So and then you consider this new. We could look to the periodic states. It's possible, and we have results in the sense. We can prove that if you do the same setting, but instead of considering translation invariant, you take, for instance, some period 2, for instance, and then you consider a model that is translation invariant, but you minimize in the set of the periodic states. You can prove you have you can break the translation invariant in the sense that the minimizer is not translation invariant, even though the model is variant. It's only periodic. You have waves, like thanks to waves. It's fundamental. Of the mean field, actually, if the model is purely repulsive, then typically it's the minimizer is unique because the function is strictly convex. But you cannot conclude from that you have short range correlations because you don't have a phase. So this unique point is not necessarily ergodic in the set of all translation variants. Even under uniqueness, you could have something that has long range correlation. In the general case, it's very difficult to prove that have uniqueness. Only for specific models, of course. No? We don't have general results about uniqueness, but we should consider some specific model and then analyze it precisely. But in the purely repulsive cases, in general, you have uniqueness, and then you have to prove that whether you have a phase or not. At this point, is extremely. Thank you. Sorry.